There we go. Doing that. Wait, I better double check it. La la. Well, yeah, but my audio. All right. All right, I will begin with a word of prayer. Ahem. 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 Heavenly Father, we thank you for this day. Thank you for the break that's about to start. Help us to just use this time wisely to glorify you, Lord, in what we do, Lord. In my prayer, Lord Jesus. Amen. So there's the exciting Top Hat code for today. I do have a few things to hand back to you guys, mostly bonus stuff. Let's see here. Sam, Megan. Jeff in the back. Let's see here. Let's see here. Sam again. Megan. Katie.
She's not here.
Not here. Ernesto. Oh, sorry. Lydia. Landon. Matthew. Sophie. Oh well. Justin. Up in the front. Jacob. Sarah. Danny. Who's not here? Simon. Sam. Other Sam. Uh-huh. I will say, excuse me. I think the bonus question. I mean the problem 60, 61. I think the answer is simpler than like a lot of you found, but I'm not 100% convinced of it yet. So when I figure that out, I'll share it with you. All right, I'm just saying. But I've seen enough to know that your solution is like, it's a legitimate solution. I just think there's a little bit more to do with the math. All right, enough about that. Any questions about the material we're currently covering? Anybody? All right. So here's a hypothetical problem. Suppose you you got a grinding wheel, all right? All right. And then let's suppose that somebody uses it to sharpen a tool, all right? And suppose they use it to sharpen a tool. Well, okay, so let's suppose it's, it's spinning with angular velocity omega equal to, let's say 300 radians per second. So it's really moving, all right? And then there's some friction, all right? There's some friction in the bearings to this wheel, this grinding wheel, all right? So it slows, all right? And so that's the initial angular velocity. Let's suppose that it slows to rest. After, let's say, 30 seconds. All right. And let's suppose that's by a friction force of, let's say, 1 Newton applied at the edge. So I decided against the bearings. I said, instead of the bearings, let's say that it's being slowed by like a brake that's applied right here, okay? I know you got some kind of thing, you put your pedal on it, it brakes it, right? And so let's suppose that the radius of this wheel is what? What do you want to make it? Let's say it's 30 centimeters. Oh, but we've used 3 too much. How about 40 centimeters? It's a pretty big wheel. And I think 1 Newton seems too small to me. Let's make it a little bit more exciting. Let's see here. What's the weight of a small child?
That's a great question. You have kids.
How old are you?
Let's see. I suppose you have a 30-kilogram child. What's its weight?
Oh, 60. That's a good size.
It's a good size? Yeah. So if we make gravity 10 meters per second squared, then we got what? 300 newtons, right? So that's roughly speaking the weight of a small child. Medium-sized child, maybe. All right? So, what's my question? My question is, what is the moment of inertia for the grinding wheel? So how should we figure this out? Any ideas? So you know that its initial angular velocity is 300 radians per second, right? It comes to rest. What's its final angular velocity? 0, right? We know the time, so what can we figure out? We can figure out the angular acceleration, right? Alpha is omega f minus omega naught divided by, delta t, which in this case is minus 300 radians per second divided by 30 seconds. So we get what? We get minus 10 radians per second squared. That is our angular acceleration. All right. So how do I figure out the moment of inertia? How is moment of inertia? Can you figure out moment of inertia directly from angular acceleration? You can't, right? Yep. Oh, right. So we need to figure out the torque. The net torque, right, is equal to I alpha. Now, question. I'm not assuming that this is a grinding wheel in space, right? I'm talking about a grinding wheel perhaps on the surface of the earth in somebody's machine shop, whatever, right? Before electricity stuff. I mean, this is a human-powered one, right? Whatever. But why does gravity not matter in this problem? Why does gravity not put a torque on the wheel? Yeah.
It affects one side of the wheel going down the same as it affects one side of the wheel going up.
Exactly. The left and the right sides of the wheels are experiencing equal and opposite torques by gravity about the center, right? Because the right side of the wheel is pulling down this way, the left side of the wheel is pulling down that way. But as long as the wheel isn't asymmetrical, right, the net torque from gravity would be 0. That's why it's important it's balanced, right? Because if you had a lopsided wheel, you could have, you could actually have torque from gravity depending on how it's situated, and that would make it like wobble, right? So the net torque is equal to what? The force times the distance, right? So here R times F. And the radius is what? So this is the torque in this case. And so the radius here was 40 centimeters. Now we want to convert that to meters, right? So how many meters? 0.4 meters. What's my force? 300 newtons, right? So the torque that we're looking at here is what? 120 newton meters, is that right? Justin's not even going to pick up his calculator for this one. Am I right? Okay, good. Just checking. It's that time of the week. It's that time of the semester. I need to check. All right, so 120 newton meters, that's going to be equal to I alpha, right? We don't know what I is. We do know what alpha is. And of course, what's happening? You give it a friction force, right? So if the rotation is this way, right? What way is the friction force going to be pointing? Think about it, right? So if the motion's like this, the friction force is going to be pushing like this, right? And so if you think about it, it's creating a torque in that direction, right? It's creating a torque in opposite the direction of omega. In other words, this torque we should think of as being negative, you know? Now, putting the sign in like that, it's kind of a matter of taste. You can also, for example, the teeter-totter thing I had last class, sometimes it's more reasonable just to say the torques have to be equal and opposite. They have to balance and not so much sweat the details of the sign convention. But sometimes we have to sort through the sign convention, so just thinking about it here. So what I have then is I've got minus 120 newton meters is equal to the moment of inertia, I don't know, times minus 10 radians per second squared. And what do I get? I get that the moment of inertia for this wheel apparently is what, 12? What do we got? So what's the deal with radians? Radians isn't a real thing. That's just put there to keep track of the fact we're using radians. You can think of it as just, it's a different thing than per second squared or newtons or meters, right? So essentially you can drop the radians in the calculation of the units here. And we have 12 Newton meter second squared. What's that work out to? What is a Newton meter times second squared equal to? Can you guys tell me?
Kilogram meter?
Right, this is 12 kilogram meters squared, right? Because there's the Newton is a kilogram meter per second squared. The second squareds cancel, and we're left with that. That's the units for moment of inertia, right? What was the moment of inertia for a point mass? Just to review, I equals mr squared for a point mass, right? What's the moment of inertia for a cylinder? 1/2 mr squared, right? Solid cylinder, of course. But my larger point to you is that the units for moment of inertia should be kilograms times meters squared, all right? Does this make sense? I hope. Here's another question. If the grinding wheel is actually a cylinder, right, what's its mass? Can you guys tell me? So what do we do? It's pretty simple. Given everything we've already done, you do what? You put 12 kilogram meters squared equal to what? yeah, 1/2 m r squared. And what was r? R was what? It was 0.4. So apparently the mass of the grinding wheel, if it actually is like I say here, is whatever 24 kilograms divided by 0.4 squared is. What'd you say? 60? $150? I now have 2 votes for 150, so by consensus, the answer is 150. Very good. So, as I've talked about before, math is done by consensus, much like physics, so it really comes down to a vote. If you have a new theory of physics, it's important you know, amass a large following so that they'll vote for you. This is mostly a joke, but not entirely so. Anyway, so here's an example. You guys have any questions about your homework? Yes, no, maybe so. All right, well, let's go on then. So, another example. Here's another example I could ask you. Suppose you have a wagon wheel. All right? You have a wagon wheel like this. And let's suppose it has, oh, I don't know, how many spokes do you want to give it?
6.
Is there a homework problem on this?
I have no idea. I genuinely have no idea.
Okay, 6 it is then. Wait a minute. I think we're going to have to give it 8 because my 6 is outside my artistic abilities. 8 I can definitely do. 9? No. I think pride comes before the fall. I said I could do 8. I'm not sure about that either. Let's just gloss over that with one of these deals. There we go. So my question for you is, what's the moment of inertia of this wagon wheel about its center? Can you guys tell me? So if I tell you that, you know, it's radius r, let's say, and let's say that the mass of each spoke is, oh, I don't know, 3 kilograms, and the mass of the rim is 10 kilograms, right? And I'll put a number in since I'm feeling numerical today. Let's say r is, what's a good radius for a wagon wheel? It's kind of before my time. Any of you farmers? No? Half a meter, okay, 0.5 meters it is. So what's the moment of inertia for this then? How would you figure it out? I'll do the easy part. The moment of inertia is equal to big M r squared plus 8 times something. So here I'm talking about, of course, the mass of the rim is big M. I'll make the mass of the spoke, I'll make it little m.
1/3 ml squared.
Now why do you say 1/3 ml squared?
Because that's the moment of inertia for us under the rotating axis that's perpendicular.
Okay. Is it at the end of the, at the end? Okay. And so L is equal to what here? R, right? But yeah, 1/3. So you said 1/3 little m, and L is R here, so R squared. And so there you have it. This is how we find the moment of inertia for a wagon wheel. So if I ask you a question about a wagon wheel and its kinetic energy on the test, let's not be like, why you do that to me? Like, you should be like, thank you, sir. That's an easy question. Woo! And then, let's see, your 0.5. I mean, I guess it's easier if we've done this. If I haven't done this, then it's a less friendly question on the next test, isn't it? Wait a minute. Do I square kilograms? That seems wrong. Meter. And let's see here then, plus 8/3. And what do I got? I said 3 kilograms. Hey, that worked out nice. That was an accident. 3 kilograms times 0.5 meters squared. The 3's cancel. You get 8 plus 5, so 13 times 13 kilograms times 0.5 squared, whatever that works out to, yeah? Is it 3.25? Kilogram meters squared? Am I right? I await the judgment of Justin.
I think it's 18.
Dang it. It's 18? See, I was trying to do the, oh, yeah, I did the, curses. Yeah, 18. This is what I get for not getting my calculator out. So 18 times 0.25. So 4.5 then, yeah? All right. All right, so let's talk about torque then as a vector. So the proper definition of torque, all right? So definition, torque produced by F about a pivot point is given by the radial arm, R vector, crossed with the force, and that's the cross product. So the formula is this. The torque as a vector is equal to R cross F. To be more, a little bit, here's a formula for it. What we're talking about is RF, the sine of the angle between them, all right? I'm going to use phi here for a second. And then a unit vector, let's call it n hat, where this is given by the right-hand rule. Right-hand rule. So let's see here, example 3. I always like to think about a door. All right, so think about a door. And I'll put the door on the at the origin of the coordinate system x, y, z, right? And I want to think about, and maybe I should have made my door, I should have been less ambitious. I should have just put the door on like the, maybe less fancy, and put my door in an easier place to think about. Let's put it in the plane of the, let's just put it in the zy axis, zy plane. Here, all right? And let's think about putting some forces on the door. What kind of torque are we going to produce? For example, if I take and I put a force like this, right? And what I mean is suppose I put, basically I'm being very stupid. I'm just going to, this works better if I have a door in the front of the room. This classroom isn't always miserable. This is the worst classroom to teach physics in that there is at this place. Like, you guys are so spread out. Half of you are working on your laptops. The other half of you aren't paying attention. That's not true. Reduce those fractions. A sixth of you are not paying attention. The other sixth are working on your laptops. The other, what am I left with? 2/3 are paying attention. There we go. That's better. But, so, I have to go to the back of the room pretty much, but I think this has to be done in the hallway. So if I go back here and I pull on the door, nothing happens, right? Nothing. On the other hand, if I pull on the door, it closes it, right? So if you pull on the axis of the rotation, nothing happens. Let me put this into a formula. So what would this be? This would be something like 0, F naught 0, right? Where's my radial vector? If I apply this force, the radius arm is right here, right? So what's R in this silly picture? R would be something like, oh, I don't know. It's not going anything in the X. And it's got, you know, Y and Z are non-zero like that. So what happens when you take the cross product of this thing? I think I actually do produce some torque here, actually. Huh, interesting. What is this one? R cross F, what do we get? So I need to calculate. Let's see, let me put it back into other terms. This is y hat plus z hat. Cross product with F, which was F naught y hat, right? You remember our rule, we have x hat, y hat, z hat, and we can talk about the cross product. So like the cross product of y hat with y hat, this piece just gives you 0, right? But what's z hat cross y hat?
Negative x hat.
Yeah, negative x hat. So I actually do get minus z f naught. Yeah, just what you said, x hat. So the torque, in my silly hypothetical example, is minus z f naught 0, 0. This doesn't seem right to me.
Well, your pivot point is about the origin, so you're pulling the door down on its hinges.
Ah, right. So to be fair, I should have put the door like, to be fair, I should have drawn the picture like this, right? more like this. I should have put my door half below the y-axis, half above like that, you know, and something like that, right? If I'd done that, then we would have gotten 0 torque. So this right here would have been my radial arm, right? And then this is the force. In this case, you can clearly see that the torque was R cross F, and that's equal to what? I have no regrets. It's good to go through an example here like that. I'm a little bit perplexed on why the direction of the torque there. I don't quite understand it. Well, anyway, I'll come back to it in a second here. So this one here, R cross F is 0, right? So the torque is 0. Like, see, if you can picture where is minus z x hat in this picture? It's what? It's like, it's right out of the board. So actually what's going on here is there's a piece of this force which is going down like this, right? This is the perpendicular part of the force to the radial arm, and what you're doing is you're creating a rotation in this sense, right? So the rotation is in this sense. It's going in the sense of the rotation is into the board, which is why we got a negative there, because x hat goes out of the board. So it's a negative torque in the sense that it's creating a rotation like this around the x-axis. Keep in mind the x-axis goes directly into the board. So it does make sense. It's just, anyway. Okay, so this is our definition of torque. It's R cross F. Now what do we do with this? Well, the next thing to do is to talk about the analog of momentum, all right? So we've talked about, torque is equal to I alpha. This is true. Although it does, so when you write the vector torque is equal to I alpha, what kind of alpha? You have to give the alpha also a vector direction. What direction do you give if you're going to write, torque is equal to I alpha? What direction do you give the angular acceleration if you write such an equation? And conversely, that's I times what? D omega vector dt. How should you think about the direction of the angular velocity? Yeah. It does have to do with the right-handed rule. But I mean, this is the question is like, what is, if I, specific example here, if I have, a mass here, let's say, and suppose it's, rotating around the z-axis, all right? Or if you like, here's a better picture. Here's the circle that the mass is traveling in. Here it is, right? It's going around like this, all right? What is the angular velocity vector of this? And suppose that this distance right here is r, all right? So if that means that the tangential velocity is what? V is r omega, right? What direction should we say that the angular velocity has in this case? The right-hand rule is the right answer. So you curl your fingers in the direction of the motion. The way your thumb points is that defines the omega hat, the omega direction. So here, omega should points along axis of rotation as given by right-hand rule. So now, to be more careful, like we can talk about rotational motion with respect to an axis. So I could also ask, like, what's the angular velocity of this mass with respect to another axis? And that would be perhaps very complicated. So it's most natural when you actually have rotational motion around an axis and you just ask, what's the angular velocity, all right? Okay, so that's the sense in which we apply vectors here, okay? And we try to keep it scalar as much as we can, like all of the examples I've done, like the start of today. I don't want to talk about vectors there. It's kind of relevant, right? So next definition is angular momentum. And we'll start out by talking about the angular momentum of a mass, point mass, m, with velocity v with respect to origin, given origin, all right, such that it has position vector r. So when you're talking about angular momentum, you need to anchor it to some origin, all right? But in this context, we use the symbol L, capital L vector. It's equal to r cross the momentum of the vector, actually. Now here, what is the momentum of a point mass? This is pretty simple, right? It's just what? M times V. So we can also write that this is equal to r cross mv. All right? Now if it's a point mass, the mass is constant, right? So the constant pulls out of the cross product, and we just have mr cross v. So what's the usual formula here? In terms of a unit vector and the right-hand rule, we could write this as m r v times the sine of the angle between the, the velocity and the position here. So I'll call it phi for this lack of imagination, n hat, where this is given by the right-hand rule. Any questions? So, all right, this is angular momentum. So the interesting thing to do here, of course, is to calculate the time rate change of the angular momentum and see what we get, all right? So let's do that calculation. And actually, I think this on its lonesome, you're kind of like, well, why are you defining it that way anyway? All right? So I don't think it gives an answer for why it's interesting until we do the following calculation. The following calculation makes this interesting. All right? So in particular, if we calculate dl dt, I'm going to do it up here since you guys see it better. dl dt, what do you get? ddt of r cross p. So the interesting thing is there is a cross product. There's a product rule for the cross product. So just like there's a product rule for, a dot product, there's also one of those. There's a product rule for the cross product. Now the rule for the cross product is you have to be careful of the order. And so it goes like this: dr dt cross p plus r cross dp dt. Now what is dr dt here? Remember that the velocity is dr dt, right? So what we have is the velocity crossed with the mass times the velocity plus r cross dp dt. Now I'm doing all of this for a point mass just to get us started. Like in a future lecture, I'll talk about how this works out for a rigid body, for a system of masses that are glued together who share a common fate of motion, right? Like an actual material object. But let's start with a point mass. That's what we're doing. How does this work out? What's going on here? What's v cross v?
0.
Yeah, v cross v is 0 because any vector cross with itself is 0 because they're, that's property of the cross product, one of them. And what's this over here? What is dp dt? What is that? We talked about this, right? Newton's second law in terms of momentum is just that the force is equal to dp dt, right? So what we have here is r cross f. What is r cross f?
Torque.
That is torque. So what do we have? Now this has to be the net force, right? That has to be the net force on the mass, and this likewise has to be the net torque on the mass. But this, right now, we have now found the proper vector analog of Newton's second law, namely that dl dt is equal to the net torque as a vector. Now this makes for all kinds of interesting problems going forward. What do we get to say if the net torque is 0? Right, then dl dt is constant. In other words, angular momentum is conserved, right? So angular momentum is conserved if the net torque is 0. So of course that's not especially interesting for just a single point mass, but it becomes more interesting when we're talking about a system of masses where you can trade angular momentum from one piece of the part of the system to another, right? Let's see here. Oh, he's really noisy over there today, isn't he? Must be something exciting. Let's see here. Well, these examples, I mean, we'll get back to the angular momentum. I probably should show you a couple of these examples before we finish today. Actually, it's up to you guys. Would you rather see more kinematics, or would you rather have an example of angular momentum? What's that? What did you say? I just didn't hear it. Nothing? Oh, man. You guys have no preference? All right, I guess we can end early today then. But is that acceptable? All right, so I'll stop now then. I have gone over a bunch of times, so I think I owe this to you.